Okay, let's start. So we're very happy to have Federico Rodriguez-Hertz. The title I don't remember, but that is super.
Yeah, receive boundary or so, something like that. So yeah, we will see. Okay, thank you very much for being here, and the invitation is always a pleasure to visit here. Okay, so let me start stating a result, which and then I will start with the history of how we get into this result. So we were not actually looking for this particular result. It was a byproduct of what we were trying to analyze. So let's first joint work with Aaron Brown and Wang. It's a work that started long ago and is still ongoing. Let me just start easy. So we take gamma, a lattice in S7R. And we look at an action of gamma, let's call it alpha, by diffeomorphisms, say, infinity CR of a manifold n. The dimension is exactly n minus 1. So it's very low dimension here, n otherwise is true, but n is meant to be at least 3, so the dimension is at least 2. And R is also has to be strictly larger than 1, but it's infinity is fine. And then the theorem says that, okay, maybe before stating the theorem, let me give you 2 examples of such actions. So, example 1 is always just very trivial action, but it's an action. So, and the second is a little bit less trivial, is you look at the projective action. So RP2 is space of lines in R3 to the origin. And well, since this space of lines, SLNR naturally acts Rn. And then SLNR acts naturally on this space of lines, and so you have this acting by removing the lines, and you can restrict them to your lattice inside the gamma. Okay, so you have this, and then you have the other, which is the double cover of this, is the sphere Sn minus 1, which is the space of oriented lines, half lines on half rays on Rn. So, and that's the theorem at the end of the day. So theorem says if alpha is an action as above, then either 0, it's 1 there, the kernel of alpha is finite index, in gamma, so it factors for a finite group, so that will be the 1, or M is diffeomorphic RPN minus 1 or SN minus 1, and the action is loosely conjugate. Okay, so that's these are the only examples. Now let me give also one more, because restriction of these guys, but that's how you reach to them through this theorem. So let me just do SL3, and I will try to focus in SL3 almost all the talk. Yes, all the rest of things, and actually things can be extended to some extent to other groups, but then one needs to understand. So the proof extends quite a bit. Now, what the proof is telling you, that's less clear. But in this case, it's a clean statement. In the general, it's just some statement that, well, it may be hard to explain. But for SL3, everything is nice and simple. So you have two very important groups, Q, which is essentially these groups of matrices, where this entry is, say, positive, and then you have the other one, which is U is 0, 0, and now you just allow positive and negatives. This is your G. Now when you do G mod Q, you get RPN minus 1. When you do G mod Q plus, you get this figure SN minus 1. Okay, so that's the main difference between both. But what is important is that actually you get this as an example. It's not really you restrict to gamma an action of G on these spaces. You have G acting on itself, and then it goes down. So you have gamma then restricted to an action on itself, and then it goes down to this quotient action on G mod Q and G mod Q plus. And that's how you will uncover it somehow. Okay. Now how we reach this type of statement? So let me show you one more important action, which is not in n-1, is in dimension n, that will essentially play no role in this talk, but this plays a very important role in the history of what we were doing. So you take gamma is SL and Z, and then a gamma, you can make it in the terms Tn, which is 1n, not Z. Okay, and so there are a main difference between the action in 1, the action in 2, and the action there. So this action is finite action, so it's essentially identity element. So it has plenty of ergodic measure. Essentially, if it is just identity, then every measure is invariant. Otherwise, you just need some finite symmetry. In the item 2, there is no invariant measure at all. So for the gamma action. And the reason for that is very reasonable. Let me even draw it in the circle. In the case of SL to R, you pick any element here, hyperbolic, so diagonalizable over R. So it has two fixed points, and that's it. The invariant measure is either this guy or that guy. So these are the only possible invariant measure, or a linear combination of the two guys. And then you just conjugate this gamma by an eta gamma, eta inverse, so that the eta send these 2 points here. So then the measure is either supported here or supported here, but it cannot be in both places. So that's it. That's it. It's a very easy, straightforward explanation why there is no invariant measure. It's not the type of explanation we are looking for, because what we were looking for is to answer the question is one, when this action has an invariant measure. Okay, so how can we, it's even more than when, so we were really willing that every action has an invariant measure. So we know it's not true, but we really wanted it to happen. So we had a huge line of ideas that started with, let's start with an invariant measure, then we do this, we do this, we do that. And we really wanted very badly the invariant measure. And then there is this guy which has an invariant measure, hard measure is invariant. Then you have all these periodic orbit, finite orbits, they are all invariant. And there are essentially not more invariant measures than that, but that's already quite a bit amount of invariant measures. And okay, so after a while, we did two things. One is we say, okay, let's start with invariant measure. They assume that the action is volume preserving. Why not? So people study just volume preserving action. And still we got stuck because we started making a lot of analysis. We get open set, even an open invariant set where we could do a lot of stuff, but then you have the complement, which is a closed invariant set. And then you go back and say, okay, now I want a measure inside this closed invariant set. And we go to step 0 and say, okay, how can I show there is an invariant measure on this closed invariant set? So, and again, gamma is not amenable, so it's really a very bad guy. So we keep thinking, so why? This guy has invariant measure, the boundary does not have. Until Sheeran essentially said the magic word and said that resonance is the magic word. Resonance is the explanation to why an action will have an invariant measure no matter what, or or it may or may not. It's up to the action. So what does it mean resonance then? Yeah. So in general, when you have a representation of the Lie group, you have the weights of the Lie group. Okay, but here we don't have representation, we have actions on a manifold, but that's more or less the same as a representation for most of the time. So we have what are the Lyapunov exponents, which is the same as the weights. Okay, now it's Lyapunov exponents of whom? So you do the following construction. So you have the gamma is the acting guy. We want to extend to a G action. So we just take G times M and quotient by your gamma. So yeah, GX will make it. Use on this space, so you quotient by this relation, and then you can just add A times GX is. So you just do this. So you call this guy M alpha, and this M alpha fibers over your G mod gamma, and your G actions here fiber over naturally the G action down there. So you have fiber M's and the G mod gamma in the base. So the G mod gamma in the base is the same action of G mod gamma that we all know, is very well understood. And the action on M is still a mystery. And when you go to the fiber over identity, the stabilizer of the identity is gamma here, you just recover your gamma action when you,
What's the energy equals H here? What was it?
is this A times G, so you just multiply in the first coordinate.
What's A?
A is any element in. So for every,
Okay.
okay, so you just act now for the G action, so. No. So you have your fancy right here, and then you have your tori or whatever manifold started with up there. Okay, so you still land in the same problem, but the advantage is that G rather than gamma doesn't have such a large guy, while G contains a subgroup P, which is now P should have been described when the Q was described. P is this guy. So this is P. Essentially the largest amenable subgroup of G, and so we have a P invariant measure. So there you are, your starting guy, the new P invariant measure. Okay, I still call, so I typically note it this way, and I still call this action here by alpha. And so P is alpha of P invariant. Okay, so these measure mu's will project into G mod gamma to a P invariant measure. And there is only one P invariant measure on the G mod gamma, which is Hart measure. So it projects into Hart measure.
Why do you have a P invariant measure?
Because, okay, so there is a couple of subtleties. So essentially, P is amenable. So in principle, if the M alpha were compact, you just average and you are happy. If the M alpha is not compact, the reason of non-compactness is because of the G mod gamma. And actually, you essentially have your Hart measure downstairs, you put Hart measure downstairs, and your averaging is only happening in the fiber, which is compact. So life is nice.
But M is assumed to be compact.
M is assumed to be compact, yes. Yes. Yeah, otherwise, okay.
Unless it's compact.
Okay, so you get this P invariant measure, and actually, it's enough for what I'm going to say to have an A invariant measure. The A here is the diagonal guy. And the A is abelian, which is even better for what I'm going to write. So, which is the Lyapunov exponents. So what you have is that the tangent on M alpha recomposes as some at every point, decomposes as some directions, one which are the Aij directions, which come from the base, and then others which will be some of the weights essentially of the Lyapunov exponents on some lambdas or F lambdas. Okay, so this is in an alpha restricted to A invariant way. Okay, so it's not P invariant, it's A invariant, only the splitting. So in the sense that when you take the derivative of alpha at some point x, call it x bar, of A in one of these guys is exactly the Aij alpha A X bar, and the same with the F lambdas. Okay, now I'm making this splitting already typically oscillated, so this is pretty much oscillated still, and give you this splitting, and then it will tell you what happened with the growth of vectors here. So it tells you that the limit as n goes to plus or minus infinity of 1 over n log of, and now we'll write what happened with the second part, dx alpha a of v alpha a power n of v. This limit is exactly this lambda evaluated at a. This is if v belongs to the f lambda guy, and here lambda is the functional, it's the weight from A to R. Yeah, this is for every A for almost every X. With respect to your new measure, new almost every X. Mu has to be assumed ergodic, so once you have a measure, you can assume it's ergodic. If it is P ergodic, it is A ergodic, so this is all fine. So these are essentially the weights with respect to this invariant measure of your guy. So these are the weights. The Aij are not so fun because if A is e to the T1, e to the T2, e to the T3, then the AI in the Aij you have the roots Ti minus Tj. And actually corresponds to the corresponding directions as already so. So this splitting here corresponds in the picture. So the Aij's are tangents to the G orbit, and the F lambdas are tangents to the fiber. Okay. The sum of F lambda is tangent to the M over the corresponding G in the base, or G gamma in the base, and the sum of the Aij's is the tangent with the Liachen. Answer. Okay, now I can really say what a resonance is, because now I have the lambda. So, okay. Okay. Is resonant exists lambda fiber component such that and is positive such that lambda equals to S times. Is a constant multiple, positive multiple of one of the guys. So it's resonant. Okay, it's a matter of taste of taste. So you could define resonant if you have a constant positive or negative, you don't care about it at all. But for what we care, the positive proportional are really the important ones. So that's the resonant guy. And the theorem says it's quite general, but that so it has to be pretty much the setting before that you don't care about restriction on the dimension, but you do want to start with the gamma action and go to the induced action and take a p-invariant measure. So the invariant measure according to Affiliation. Actually, it's enough to be A invariant. Let's see. We'll have infinite values. Invariant measure. 4. So if R ij is non-resonant, or non-resonant means that it's not resonant, so with any Lyapunov exponent, then mu is invariant under the group Ui. The roots group associated to that. So then in order to get invariance along this direction, you want it to be non-resonant. Okay, of course, you already guarantee the invariance of the P if invariance by all the guys above. So maybe the guys above are resonant or not resonant, you don't care because you already know invariance there. So you really have these 3 entries here. You have these 3 possible entries, and you really want to ask yourself, okay, is any of these guys resonant or not resonant? Okay, so let me show you how easy you get an invariant measure now. So dimension 2. So you have potentially 2 Lyapunov exponents, lambda 1 and lambda 2. Okay, so you know your measure is invariant by the diagonal, is invariant by the guys above the diagonal, and now you start with this guy. Okay, so maybe let's start with these guys. So you look at this guy and you ask yourself, is this resonant with any of them or not? And okay, if not resonant, then you get a D6 invariant. Otherwise, you have that this is 2, 1 is some S times lambda 1. Okay, they go to the next one. Okay, so you go to R3, 1. Okay, cannot be the lambda 1 because it's already taken. So if any, it will be the lambda 2. Yes, D1, lambda 2. Okay, the last one has to be invariant. There is no more roots to play. Okay, so you get this. Okay, actually, if it was dimension 1 instead of 2, I get at least 2 of the guys, which will have some extra invariant because I have only 1 Lyapunov exponent to be taken. And so if it is taken by this, then the other 2 give invariance. But then the measure has to be invariant by a subgroup because being invariant makes it a closed subgroup. So if it is by any 2 of these guys, is already invariant for everybody, and it's G invariant. So here you get the following dichotomy. Either the measure is fully invariant, or it is invariant by Q, or it's either corollary, either mu is G invariant, and then you are happy because if it is G invariant, you can restrict to the fiber by identity essentially, and then you get a gamma invariant measure. Or still mu is Q invariant, and you adapt this condition. So you get this, you gain this knowledge. The Lyapunov exponents are multiple of these guys. And this. These are the two bad situations. Okay. So let me explain briefly how the proof of this guy will go. So you start taking p-invariant measures, take all possible p-invariant measures, and if you always get that the p-invariant measure is G-invariant, then you will get that since it is G-invariant, you have Zimmer cocycle super rigidity that tells you that the derivative cocycle is actually equivalent to a representation on dimension 2, but there is no representation of SL3R in dimension 2. Okay, so then they are, it's only the trivial one. So you get that all of them are trivial, which means that the Lyapunov exponents actually have to be trivial always. And then that's exactly what the theorem of Brown, Fisher, and Hurtado need to prove that the action is action by isometries. So if you know that every p-invariant measure is G-invariant and all these representations are isometric, then the action is by isometries. And in this low dimension, action by isometries means that it has to be a finite action. So there are no isometries. So that's what happens if no matter which p measure you took, you got this G-invariant. So what's happening is if you're not getting this trivial guy, is because you encounter a p-invariant measure that was not G-invariant. And then you gain the Q invariance and this extra two condition. Okay, so this still requires the proof of this theorem, but instead of trying to explain you how to prove this theorem, I will continue with how you argue in the proof here, which has, in a sense, hidden what is the proof of this as well.
The rules for this, for the action on the suspension.
Yes.
The projective space.
Yes.
They are resident.
Yeah, exactly. They are exactly these guys. It's Ti minus Tj. So it's okay. Yeah, that's a very good point. It's nice thing to see. And try to draw the picture. So here you have R3. So since I described the Q as quotient by this guy, so the sphere or the projective space are quotient by this guy. So I have the first direction, which is this line here. And so when you look at how, okay, this guy, look at the sphere, will be this point here. And when you act linearly in R3, so vectors here will get expelled or contract to this direction. And what is the rate? The rate is the e to the T1 divided by e to the T2 when you stay in this plane. And when you go to this plane, you get e to the t1 minus divided by e to the t3. So that's the rate where you get contracted on this equator or on this equator. So this equator corresponds to the vectors in this plane, and this equator corresponds to the vectors in this plane. And we take a direction here, and you start iterating by your diagonal matrix, just get approximated to this guy, assuming that T1 is larger than T2, typical direction. So then you get approximated at this rate, the quotient of these two guys. Okay, because essentially you have to it's better. So you send the 1, 0, or the 1 x 0, you map it into e to the t1, e to the t2x 0, and then you go and normalize it 1 e to the t2 minus t2 x 0. Just get multiplied by this, which means that the Lyapunov exponent along this direction is exactly this t2 minus 2. It's exactly the R21 without proportionality, actual proportionality equals to 1. And same with the other, you get exactly the R31. So yeah, that's very important. Actually, that's crucial from how to get the second part of the theorem. The fact that that's exactly what's going on. Okay, so the fact that this Ocellet's theorem comes together with not only the splitting of the bundle, but it also comes with invariant manifolds. So you can integrate these bundles. And so there are a couple of rules, which means that you essentially can integrate whenever you can make all the guys negative or all the guys positive. So you pick a direction, any A, you define A as A, which is the sum of EIJs, where Rij of A negative, plus the sum of F lambda, where lambda of A negative. And then this guy will be always tangent to a manifold, which is mu almost always. And these manifolds are disjoint from each other. They give a partition of the guy, and of course, if lambda of A is negative, you take the A inverse, it gives you positive, so you start playing with A, and if you move a little bit the A, this doesn't change, so you essentially have as well a Veil chamber partition into Veil chambers of the A's where the guys have the same sign. Okay, now you can start intersecting these guys. Take maximal or minimal, rather maximal. Depends on what you mean, maximal, minimal. So, but you just the intersection, non-trivial intersection of smallest possible dimension, and you see that when you take the intersection, you can isolate this. Let me just, you can isolate all the EIJ, where the IJ corresponds to the upper place, I guess is I smaller than J, I guess corresponds here. So the upper guys. There is some guys here, actually I forgot to add them here, which is the diagonal guy, right? So the tangent to the A. That's no one ever cared about them. So this guy can be isolated, then I can also isolate the guy which is non-resonant, And that's exactly why non-resonance show up, because you can isolate it this way. So it's A to 3, just by intersecting this guy by different choices of A. And then finally, I can isolate the E to 1 plus F lambda 1 and the E 3 1 plus F. So I can separate this guy, and the way I separate him, as I said, is by intersecting by different values of A, these guys. And each of these guys are tangent to the corresponding intersection of manifolds. Let's see what's going on in this situation. E to 1 plus H lambda 1. So it's a two-dimensional space. And the W to 1 is tangent to this guy, is a two-dimensional manifold which contains a one-dimensional subdirection. So this is the point X bar. So this is the U21 orbit. So this is the group tangent to the space. So you have the U21 orbit through X. This gives you this manifold, which is through the G direction. And then it also gives you some W21F, which is intersection of these two dimensions with the fiber. So I have these two very canonically and well-established options here. And not only I have it through this point, I have through every other point here. I have an horizontal, which is orbit of this guy, and a vertical, which is the corresponding fiber. Okay, so then I can take this conditional measure of mu21 along this partition into W21 manifolds. And I want to know how this guy looks like. Okay. And one thing I know is that the measure mu projected into R. Okay, this is a non-trivial argument actually to claim what I'm going to say, but it is true that when I take this guy and I project it out through the fibers towards this horizontal direction, I still get R measure. Okay, so then I can try to look at how are the conditions along the fiber direction. So I can decompose this measure as an integral of mu21 fiber dr on this u21 direction, essentially. And then so these are conditional measures.
What exactly is U2?
The hard U21 is the hard measure on this that I can put on this orbit. So since this horizontal is the U21 orbit of X, there is a natural hard measure on it, which is just take the hard measure on U21 and put it over this. Okay, so I'm not saying, because that's actually what I wanted to prove before, that the measure mu21 is invariant by this guy. So, because this is the projected measure. So when I project, I still get hard, but that's exactly the key of the point, yes. So then I have these conditional measures. So this conditional measure could have been just deltas on this place, which means that actually then this measure is hard here. But then I still get invariance. So I assume the measure was not G invariant, so it cannot be invariant by this guy. So these measures are not there. And actually, what you can show two things. One is due to the contraction property on the fiber is that the measure has to be atomic on each vertical direction. So that's one thing you can prove. And the second thing you can show is that these atoms cannot be two on the same level. Because if you have two on the same level, then you get invariance by this movement, and then essentially you get full invariance by the U21. And you assume that there was not invariance by U21. This is how the measure mu21 W21 looks. It's just a graph, injective graph, measurable.
2 points on the same level will give you invariance.
Yes, okay. The way you are to do invariance there is very similar to the Katok-Spatial, Kalinin, Katok-Einstein, then the triple paper, Spatial, Katok-Lindenstrauf. This is always the same theory. So you go to the kernel of this direction, then you apply recurrence. And here life is nice because again, the measure, you see that atomic on the fiber, your system is measurably isomorphic to the G mod gamma. So you have all the recurrence and all the ergodicity. You can go to the kernel and still get ergodicity. Then you have a sequence of movement that will go from here to here. Okay, go to the limit, lot of losing cells. Your horizontal invariance. So it has to be really an injective guy. But then you still play the same game and you now do the very same trick I just described. But now that I know that the measure sits on an injective graph. Okay, it's a measurable injective graph, but now I want to show that it will be invariant by some movement, which is by a group of affine maps acting on this plane. And it's actually a group, not just affine maps, so it's affine that preserve verticals and horizontals, that on the horizontal, it's nice, because it's essentially I'm freezing the U21 direction. On the vertical, it may not be nice, but it's diagonal. So I don't know how much expansion or contraction it has. So it's asymptotically sub-exponential, but I don't know how much in principle. But I don't need to know how much because I know by recurrence that I can go and know that this point is mapped into a point here, which has this perfect control on the horizontal. And on the vertical, I know it doesn't go to infinity. And if it doesn't go to infinity on the vertical, it means that the expansion coefficient is bounded above. So that's how I bound, then I can make it convergent. And I show that then this measure is invariant by this affine map that sends this point to this point. And that's it. So once you know that the measure is invariant by this affine map, and actually every point in the support of the measure produce a movement and affine map that goes from this guy to the support, you know that the measure has to be invariant by a one parameter subgroup of affine maps. Then you have to argue a little bit more to make sure that actually these affine maps are pretty much translations. So the measure will be a measure on a line. So the fact that it's a measure on a line is extremely important because now I gain a crucial information. So this measure now on the line is invariant by my dynamics. Now when I apply my dynamics, in the horizontal, I multiply by e to the T2 minus T1. Now in the vertical, I multiply by e to the S1 times T2 minus T1. But this has to preserve a line, which is not the horizontal line, nor the vertical, nor the horizontal. It's an injective line. So the only way is that this S1 is equal to 1. Otherwise, I will not preserve this. Again, an extra information. So the rate of proportionality is 1. The guy really started to look like a projective line. And now you do the same argument in the other one, of course, and both directions. And now you can put both things together. So you just go to, to the sum of these two directions, which still can be written as a couple of intersections. So you look at this four-dimensional manifold, which has an horizontal, which is on the g-orbit, and a vertical, which is on the fiber. And I have the very same picture. Let's go. Yeah. That would be a little bit harder to draw, but still I will try. I have on one hand fibers, which was fitting, so W21 fiber, W31 fiber, and then I have the G part of the orbit where I have the U21, U3. Okay, and I have the product of this times this. This is a four-dimensional guy, which also splits as the product of this times this times this times that. Okay, and I know that in this second product, the measure looks like lines along here and then lines along the other direction. Actually, one can show that it's the product measure. So there is again a fine structure on this four-dimensional R4, and this four-dimensional R4, the measure is actually hard measure on a plane. Okay, so and on a plane, which is there is a linear map from here to here, which is linear with respect to the linear structure I put here versus some affine structure I put on this vertical direction here, and I have this linear map. It depends on the base point. And the measure is hard measure on the graph of this linear map. Now here is one very important good news. So this two-dimensional guy is a manifold, a two-dimensional manifold, but I'm inside a two-dimensional total manifold M. The fiber is two-dimensional, meaning that this is an open set of my M. This is an open set of. So I'm having a map from this R2 into this open set of M that is the linear map here. But this linear map, remember, is essentially given you by the measure. So that's exactly the measure. So if you want to recover from some very dynamical object, it is the measure. So it's the fact that the measure sits in a graph, well, it's the conditional measure along this four-dimensional object, but it's still giving you by the measure. Okay, now just to finish, what you do? Forget about your abstract action. Go to the action on the sphere, say. Do exactly the same we were doing up to now on the sphere. And you get exactly the same picture. Okay? Okay, now just make them match. So define a map from the sphere into the manifold by this picture. So you take your open set of the sphere. It is given as a patch over this guy, which actually it is this group here. So with this group, you parameterize your sphere by finitely many copies of this. So you take these guys and you map to your abstract manifold M in this way. So what I'm doing is just giving a family of patches of my manifold. Okay, now I need to check that the change of coordinate is smooth. And to show that the change of coordinate is smooth, actually what I have to show is that it agrees correctly with the picture I'm having. And that's where it is important that the measure is the patch is given by the measure. And the measure is invariant by the whole P action, actually for the whole Q action. So that allows me to show that I can actually move the guys and I still get the correct intersection. So I'm still almost finished on this, okay? So it's so that's it. So now you just cover your sphere by guys. So you fill the patches on the other hand, and everything is matching. So you just show that the guy is probably the sphere, or maybe it is a quotient of the sphere. It depends then on how much agreement or not was in your business. But then once you know it is a quotient of the sphere, there are not so many quotients of the sphere that will respect this. So then you figure out that it's just this or that. Okay, so that's essentially how you prove. And just to finish, if I convince you that this picture for this business, let me show you how you show this extra invariance. So this non-resonance implies invariance. Okay? So if there is no resonance, the picture essentially remains, but there is no vertical direction. There is only the horizontal, and then since there is only the horizontal, there is only one possibility that the guy goes to the same horizontal. So then you get invariance from this direction. That's how we do it. Okay, that's it for now. Thank you.
Questions?
Basically, you can analyze in this way other groups. Right?
Yeah. So
But the action, so what's the solution?
so okay, so you can analyze split groups. It's so when the root space are one-dimensional, it's pretty much the same. Okay, you want in principle a little bit more. So like SP is one of the problems. So you don't want two roots which are already resonant one with each other. So you have two roots which are resonant, then you get complication here as well. So still you can overcome this complication if you go to reasonably small dimension on the fiber. So then you are still good for that. But even that can be more or less overcome. So if you want the statement in general is if you have no resonant at all root, then you get that the measure is invariant. So that's any dimension, any group, anything. So that's completely true.
That was a stupid question. Where exactly did you use fucking gamma is a lattice?
Oh, well, yeah, I need. So I use the P action on G mod gamma, and so I wanted to be hard measure, and then you can only have that. But it doesn't mean that maybe something can be done, but it's not.
Okay.
Yeah, one can promote from A invariant measures even to full invariance as well with this non-resonant criterion as well. But you need the A invariant measure to project into the G mod gamma. So because otherwise it could be the invariant measure project to a compact orbit. That's it. You are not saying much away from this compact orbit. So you project to see the whole. Yeah, we have, for example, we apply the same tricks and we show you if you take essentially any boundary action and you take a small C0 perturbation of the boundary action by smooth diffeomorphisms, then it's still smoothly conjugated to the original. And essentially the reason is that you take your P measure and the C0 closeness tells you that there is no more invariance than what you had before. This essentially tells you that you can repeat the picture. You will have the correct dimensions.
Can you recap how you saw the conditional measures or interact masses?
Okay, that actually comes from the fact that there is another conditional that is important to take, which also plays a very important role in this finite part of the game, which is you take conditional along the fiber just by itself. So you look at the mu, you know that it projects into R on the G mod gamma, and then you look at the conditionals along the compact manifold fibers. But you know that the exponents on the fiber are all negative, and so this tells you that the condition on the whole fiber, which is compact manifold, has to be an atom, or finitely many atoms. Okay. So, and then then that restricts. Yeah, that actually is an important step. So that there is where you show that your M alpha is a finite extension over the G mod gamma, and then you get the rodicity and recurrence.
Okay, thanks again. Yeah.
Any other questions?
Now that's the question. What really about the case of maybe SL3Z acting on a 100-dimensional space?
Okay, we hope that we can handle SL3 acting in 3-dimensional space. So that's what we are hoping to do in finite time. Now in 100-dimensional space, I'm prepared even to see some monster action that no one thought before. So there is, of course, this Zimmer conjecture saying that they should be homogeneous or mostly homogeneous. I don't know. So you can do something here, and you can show that it has to satisfy several things, but I don't see why it cannot be quite wild. So so there is still, again, it helps if you only try to do things at the measurable level and try to prove some measurable classification. So to claim that the action should fiber over a boundary, which takes care of the non-invariance of the P measure, and then transfers to the boundary, you have a measure preserving extension. So these type of things, that's fine. But then if you want to see some more smooth classification, I'm not sure how far this can go.
But for dimension n, basically, you're trying to apply the same formula
Yeah.
of the.
Yeah, actually, we have the very same proof here. Will show that if you have a P invariant measure that is not invariant, so a Q invariant measure, which is no better in dimension 3, then there is an embedded surface.
But here you used the fact that it is.
An open set, yeah.
No, the dimension is lower.
Yes.
Because of this argument with the roots.
Yeah. Well, okay. When I thought so, I was saying dimension n, SLN on dimension n. So then this is one more dimension, it's like SL3 in dimension 3. So yes. Then you can essentially play the same game. So you have to take into account one more situation to take care of it, that you didn't add anyone at all. So that's one possibility, but that's fine. Then you really get the boundary. So that's pretty much okay. Then the other situation is again to this situation, and then you show that it is an embedded surface.
Okay.
And otherwise you have the invariance. So, okay, the fact that you have the invariance, or you have this or the other, it's okay. So, and that's gives you an explanation of what happened with the invariant measures. Then when you want to put all the guys together, it's still work in progress, but I think it is very cool. But yeah, again, it's very low dimension, so 3 dimension is still very low. So already when you go to 4 dimensions or things like that, so it's quite a disaster. And 100.
Basically, you can see the difference between 5 and.
Yeah, pretty much. Yeah, 5 is, and 100 more or less is already.
Any other questions?
All right, let's thank Federico again.